let's start the extension solutions. So in this problem here, we have two functions defined. F of x is called 2x minus 1, g of x is 3x plus 1. First thing it says is to find the inverse function of f of x and simplify. So the way we do that, especially if we're going to use algebra, not graphing, is we take the function and we write it with y equals instead of f of x equals. Okay, so this is the f of x function written with y equals. Next thing we're going to do is we're going to switch the output with the input, because basically the definition of an inverse function is the output becomes the input and the input becomes the output, because it's kind of like the backwards function. It does the exact opposite. So we basically switch the y to the x and we switch the x to the y. Now we already have the inverse function. Why isn't it really the inverse function completely? Because we need to set it up as output equals blah blah blah, because that is the way we normally arrange functions. So all we need to do is solve for y. How do we do that? First we're going to add 1 to both sides, so we get x plus 1 equals 2y. Then we divide by 2 on both sides, so then we get x plus 1 divided by 2 equals y. And there we have it. Okay, y isn't exactly on the left side, it's on the right side, but we can just switch that, right? Y equals x plus 1 divided by 2. All right, let's go to the next one. Now it says to find f follows g. Remember that that open circle is called follows. F follows g, and simplify. Okay, so f follows g means that g comes first and f comes second. So first comes g, and then we're going to take the output of g and we're going to put it inside f of x. Remember, f of x looks like this: y equals 2x minus 1. But before we substitute in the function g, we are going to replace the x with a parentheses and a blank. And now we're going to put it inside there. I think it's less confusing than replacing an x with an x. So let's do that. We're going to say y equals 2, and then we're going to replace the parentheses with 3x plus 1 minus 1. Then we're going to multiply it out. 6x plus 2 minus 1 equals 6x plus 1. So that is our composite function, f follows g. First we do g, then we put it inside f, and then we simplify. All right. If you want to, you could write f follows g of x, and then write it's 6x plus 1. Okay. Now we're going to find g follows f of x minus 1. Okay, so first of all, we're going to put x minus 1 inside the f function. Remember, the f function is y equals 2x minus 1. But instead of 2x minus 1, we're going to write 2 parentheses space minus 1. And what are we going to put in the parentheses space? We're going to put in x minus 1, because that's what we're supposed to put into the function 2x minus 1. That is the f function. Now we're going to take the output of the f function, which is this, and we're going to put it into the g function, because g follows f. So the g function is 3x plus 1. So we're going to write it like this: 3 parentheses x plus 1. We replace the x with a blank. Then we're going to simplify this a little bit to make it easier to substitute in. 2x minus 2 minus 1. This is equal to 2x minus 3. Now it's kind of smaller. We can fit it right into this blank here. So we're going to write 2x minus 3 here. Now we're going to simplify. We're going to distribute the 3. We get 6x minus 9 plus 1, which is equal to 6x minus 8. Okay, so basically our answer is g follows f of x minus 1 is equal to 6x minus 8. Okay? All right. Moving on. Ooh, this got cut up a little bit in the solution. Sorry about that. Draw a function on the grid provided. Does an inverse function exist for the function you drew? If so, draw it on the same grid. If an inverse function does not exist for your function, explain why it does not exist. Okay. I'm going to draw a typical function, and like this thing got really screwed up here. Okay, but we have this grid here, and I'm going to draw a parabola, okay, because that's my favorite function. All right, I drew a parabola. Now, is there an inverse function for my function? Okay, remember, the way you find an inverse function is you reverse the outputs and the inputs. When you reverse the outputs and the inputs, what I'm going to do is, and I just drew this line, this is my diagonal line y equals x, right? It goes perfectly through the, what do you call it, the origin, okay? And when you reverse the input and the output, what you do is you take certain points on your parabola, like here I have the point 2, 5. I am going to translate this point. Instead of 2, 5, I'm going to reverse the output and the input. I'm going to reverse the x's and the y's. 2, 5 actually becomes 5, 2, which is right here. And if you reverse every single point on the parabola, you're going to soon see that you create a lying down parabola. So basically, when you flip it over this diagonal line, you end up with a lying down function. And now, is this new function, this lying down function, is this function a real function or is it a relation? And unfortunately, it's a relation, because remember, if you do the vertical line test on a function, you should not intersect the function 2 times. And I can do that with this lying down parabola, right? So, for my function here, the inverse function does not exist, and the reason why the inverse function does not exist, inverse function does not exist, and the reason why is because vertical line can intersect function twice. Okay? Now, can you think of a function that you can flip over the line without being intersected twice? I can think of a couple functions. A straight line. A straight line, normally, if you flip it over the diagonal line, you just make another straight line. And most straight lines that are diagonal are going to have inverse functions. Another one is the like a hyperbola, which we have not studied yet. Kind of looks like that. Another one would be a hyperbola that looks like that. Okay. All right. Okay. Next one. Give the domain of h of x and the domain of its inverse. Okay. So the domain of this function, square root of x. So domain means all possible values of x. So what are the possible values of x that you can put inside this function? Well, remember, you cannot put a negative number under the square root. So basically, you can put in all positive numbers. Can you put in 0? Yeah, you can put in 0 too, because the square root of 0 is 0, right? So the domain here is x is greater than or equal to 0. Can we do the range? Let's try to do the range. So the range here would be all possible values of y. What are the possible values of y here? Well, the square root of a number is always going to be the positive square root, unless we say positive negative right here in front of the root sign, and we didn't. So the square root that we're going to get here is always going to be positive. So the y values are all going to be positive numbers. Now, is it going to be greater than or equal to 0, or is it going to be greater than 0? Well, if we put x equals 0, which is allowed, into the root sign, then the square root is going to be 0. So I would say that it's greater than or equal to 0. Okay? Once we know that the range of this function is all positive values and 0, we can figure out the domain of the inverse. Why is that? Because it turns out that, remember how the domain is all the x's, all possible x's, the range is all possible y's? Well, remember, whenever you find an inverse function, basically what you're doing is you're turning the inverse function on its side. So when you turn the function on its side, all the y's become x's and all the x's become y's. So basically, the domain of the original function becomes the range of the inverse. The range of the original function becomes the domain of the inverse. So here I said the domain is all positive numbers. The range is all positive numbers. And once I do the inverse, when I do the inverse of that, then the domain is going to be related to the range here. So instead of y is greater than or equal to 0, we're going to put x is greater than or equal to 0. Okay, of course the x's and the y's switch, so we need to switch them. Okay, that is a very messy colon, so I'm going to redo that. Okay, and then the range of inverse h is going to be related to the domain of the original function. So I'm going to put y is greater than or equal to 0. It's kind of hard to see what's happening here because in this particular function, both the domain and the range are all positive numbers. Okay. All right, number 6. The sequence below is arithmetic or geometric. Write an explicit equation to describe it and then find the 501st term. Use n to represent the index or position of the sequence where n equals 0 for the first term. Okay. I put 2 formulas here for you to use so you don't have to memorize them. One is for arithmetic and one is for geometric sequences. This one is for arithmetic and this is for geometric. Okay? How can you tell if a sequence is arithmetic or geometric? Well, let me check the space between each one of these numbers. Since I know it's either arithmetic or geometric, I know that this trend is going to continue on and on forever, okay? So, 42 becomes 39, and that becomes 36. What's happening here? Well, it looks like every time we're subtracting 3, right? 42 minus 3 is 39. 39 minus 3 is 36. Aha, I found the pattern. That is an arithmetic sequence. When you are constantly subtracting numbers or constantly adding numbers, that is an arithmetic sequence. So we're going to use this equation here. U of n equals U of 1 plus n minus 1 times d. What is d? D is the step. Okay, so since the step is negative 3, I'm going to replace d with negative 3. What is n? It's just n. Okay, in the general term formula, we just leave n there. And, I'm sorry, this is plus here. What's u1? u1 is the first term, which in this case is 42. Okay, so here is our general term formula, which I think that's what they asked us to write an explicit equation to describe it. Yeah, we have right here. Okay, then find the 501st term. How do we find the 501st term? We are going to plug in the number n equals 501, because remember, n refers to the position in the sequence or the index. So U501 is equal to 42 plus 501 minus 1 times negative 3, which is equal to 42 plus 500 times negative 3, which is equal to 42 minus 1500, which is equal to negative 1458. Is that right? 42, yeah, because 500 times negative 3 is negative 1500. 42 minus 1500. Okay, I think that's right. All right, moving on. Given the recursive rules for the sequence defined below, write down the explicit formula. You should only have the variable n on the right side of the equation. Okay, then find the 8th term. Okay, the recursive formula tells us the first term is 81, and then how do you get the next terms after that? Well, you get the current term by taking the last term and multiplying it times negative 1/3. So, if I have a1 equals 81, the next term would be a2, and it would be 81 times negative 1/3, which turns out it is negative 27. Okay, what would be the third term? The third term will be the second term, which is negative 27, times negative 1/3 also. So, oh, yuck. Negative 1/3 times negative 27, which is equal to positive 9. Okay? And so on. Okay? Now, let's try to write it in terms of the geometric sequence formula, which is un equals u1 r to the n minus 1. Yeah, by the way, this is a geometric sequence because you are constantly multiplying numbers to the previous term in order to get the next term. So the formula is un equals u1 r to the n minus 1. So u1, of course, is 81. They call it a1 here. And then the r value is the multiplier, which is negative 1/3. Make sure you don't forget to put the negative. N minus 1 is just the position minus 1. So this is the formula that we wanted. It's the explicit formula. Now we want to find the eighth term. How do we find the eighth term? Well, n equals 8. So u of 8 equals 81 times negative 1/3 times 8 minus 1, which is 7. So that is equal to 81 times, okay, when you take a negative 1/3 and you multiply it times itself 7 times, do you get a negative number or do you get a positive number? Well, it turns out you get a negative number because if you multiply a number times itself an odd number of times, you'll get a negative number. If you multiply a number times itself an even number of times, a negative number, then you'll get a positive number, right? So in this case, we're multiplying 7 times, so that means it's a negative 81 something. What about 1/3 to the 7th? What is 1/3 to the 7th? 1/3 to the 7th is the same thing as 1 over 3 to the 7th, okay? 1 to the 7th is just 7, or just 1, so you don't really need the exponent there. What is 3 to the 7th? Let's write out 3 7s and multiply them together. We don't even need the calculator for this, okay? 1, 2, 3, 4, 5, 6, 7. Okay, so this would be 9, this would be 9, this would be 9, and then there's a 3 left over. 9 times 9, remember, is 81, okay? 81 times 9, oh my gosh. This is really challenging me, but it turns out to be 729, okay? So 9 times 9 times 9 is 729. Then I am going to multiply it times 3. Hey, wait a second. Look at that. I'm going to immediately divide it from 81, which happens to be a power of 3 too. I'm going to be smarter than this. Forget this, okay? All right, what I'm going to do is I'm going to take the 81 and I'm going to rewrite it as 3 to the 4th, because 81 is 9 times 9, or 3 times 3 times 3 times 3, right? Now I'm going to rewrite 3 to the 7th as 1 over, and then I'm going to put 3 to the 7th, but I'm going to just write 3 7 times. Just like I did above, right? Now I'm going to cancel them out. 3 to the 4th is going to cancel out with 4 of these, and then I'm left with negative 1 over 3 times 3 times 3, which happens to be 27. Okay? So, that's my answer. Negative 1 over 27. Moving on to number 8. Is that the last one? No, it's not. There's 2 more. The sequence below is arithmetic or geometric. Write an explicit equation to describe it. Use n to represent the index or position of the sequence where n equals 1 for the first term. Okay. So in this case, am I multiplying numbers to get the next number, or am I adding numbers to get the next? Well, look at the difference between the first 2 is like about 7. The difference between the next 2 is like 30. So there's no way I'm adding and subtracting numbers here. When you add and subtract numbers, the difference is always going to be the same. It's called, by the way, the common difference. In this case, we are obviously multiplying, but what are we multiplying by? Well, these 2, it's kind of easy to see. We're multiplying 9 times something to get 45. 5 times 9 is 45, right? So we're actually multiplying times 5. A little bit more tricky. We're going from 9, and then we get negative 45. So are we multiplying just by 5? No, we're multiplying by negative 5. Okay? So it turns out if you test negative 5 times negative 1.8, you're going to get 9. So actually negative 5 is the multiplier. We'll say that the common ratio is negative 5 because that's the multiplier, right? It's a geometric sequence. Now I'm going to write the explicit equation. Un equals u1 r to the n minus 1. Guess what r is? It's negative 5. What's u1? u1 is the first term, which is negative 1.8. So negative 1.8 times negative 5 to the n minus 1. So there's my explicit equation to describe it. Okay. Now, use n to represent the index or position of the sequence where n equals 1 for the first term. And that's it. Okay? We're done. All right. Number 9. Last one. Both Art and Gabby plan on doing Math HL next year, and each has done 5 IXL exercises after 1 month of 10th grade math. Their teacher takes them aside for a talk, explaining that they will not be ready for Math SL according to their progress after 1 month. The teacher tells them they need to finish 1,215 IXL exercises by the end of the 6th month of class in order to be ready. Art and Gabby decide to show Mr. Tsubaki that they will be ready according to planning based on math sequences. What an appropriate way to show that they will be ready. They're going to show it with math. Art decides to progress in such a way that the total number of exercises he has completed, total every month, is an arithmetic sequence, completing 1,215 by the end of the 6th month. Gabby decides to proceed in such a way that the total number of exercises she has completed, totaled every month, is a geometric sequence, also completing 1,215 by the end of the 6th month. Find the explicit sequence formulas for each student. Okay, so Art. So basically, Art wants to do 1,215 after 6 months. Okay, so remember the formula for the arithmetic sequence is u1 plus n minus 1 times d, right? So I'm going to put the first day. Yeah, they do 5 on the first day. He does 5 on the first day. And then, or 5 on the first month. And then in the 6th month, he wants to do 1,215. So what is his common difference? How many exercises every month does he need to increase in order to get to 1,215? Okay? So let's see. 1,215 minus 5. So I'm going to put 1,210 equals 6 minus 1 is 5 times d. Now I'm going to divide 1,210 divided by 5. And that'll give me about 2, 4, 2. Is that right? 2, 4, 2? Maybe. Let's see. I'm going to do it here just to make sure. 2, 10, 21, 4, 20, 1, 0, 2, 242. Okay, so D is equal to 242. Now we're going to write the explicit sequence formula. The way we do that is we just rewrite what we put up there, except now we're going to fill everything in. So UN equals U1 plus n minus 1 times D. So guess what D is? D is negative 3. Guess what U1 is? U1 is 5. Okay? No, wait. D is not 3. D is 242. Sorry about that. Okay. Now we're going to take Gabby's sequence. So Gabby's sequence is a geometric sequence. So it's going to be using the formula UN equals U1 R to the n minus 1. Now remember, U subscript n means she has 1,215 exercises done in the 6th month. U1 would be the number she does in the 1st month, which is 5. Then R is unknown, and n minus 1 would be 6 minus 1, which is 5. Okay? So let's solve for R. Like, we're going to take 1,215 and we're going to divide by 5. That turns out to be 2, 71, 21, 4, 15, 3. R to the 5th. Now we're going to find what is multiplied 5 times to get 243. Is it 2? 2 multiplied times itself 5 times is 4 times 16 times 2. No, it's only 32, so that's not enough. What about 3? What's 3 to the 5th? 3 to the 5th is 81, which is 3 to the 4th, times 3. Hey, that's 243. It worked. Okay, so 243 is equal to r to the 5th. Well, r to the 5th, it turns out r is equal to 3. Okay, now we're going to write Gabby's sequence. It's going to be un equals u1 times r to the n minus 1. Guess what? u1 is 5, just like it was last time. And then r turns out to be 3. Okay? So like the number of exercises being completed, counted at the end of every month for what's his name? Art. For Art, it follows this sequence, and for Gabby, it follows this sequence. But basically, both people arrive at the total of 1,215 at the end of 6 months, even though they started both at 5. If you graphed it, the arithmetic sequence would start at 5, and then it would go to 1,215, and it would arrive there in a straight line, right? If you graphed the geometric sequence, it would start at 5, and then it would go to 1,215, but it would go kind of in a curve, okay? It would jump up exponentially. All right? And I think that's it.